Okay, this is the video study guide key for version number 2, hopefully to get you going. All right, so here we go. Looking at design 1, I have 1, 2, 3, 4 white squares. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 white squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 white squares. Looks like this is clearly going up by 5, going up by 5, going up by that same 5. Makes this linear straight line kind of situation. So I'm looking for all the equations down here that do not have this 5 in front of x or in that weird recursive form spot. So here we go, looking at these. All these numbers in front of x, this guy right here, this number in front of x is a 5. That means this one is good. This one right here in front of this x, look in front of that x. Don't look at any other numbers. Look in front of x. This one is 5. That's good. Over here, looking at this one, looking at this number in front of x. Again, don't look at any number. Don't look at any other number. Look in front of x. This one does not have 5 in front of x. This one is the only one that does not show the pattern. This 4x can't have that. The one underneath, this one is that weird recursive look with the 5 in the right place. So that one's good too. So obviously that 4x one is the only one that doesn't have that in the right place. So then looking at this equation that I'm using, when I'm plugging in that number to find out what I get at that step, make sure I'm using that correct equation. Sometimes you guys are using a different equation number. Use this equation. That -1, it's not a mystery. That -1 I got by taking away 5 from this 4 in the reverse order of that pattern. That's where that -1 is coming from. So if I plug in 13 in that equation and times it by 5, this is how I show it. F of 13, that's showing what I'm plugging in for x. It's just showing right here this 5, and where I plug in 13 right here, this is where I'm doing actual math on my calculator, taking that 5 times 13, and then whatever that answer is, eventually taking away 1. So 5 times 13 gives me, when I plug in 13 for x, I get 65, and then I'm going to take away 1 from that, which tells me at step 13, I'm going to have 64 white squares if I keep going in this pattern. All right, moving on. Next one. If I'm looking at this guy, this one clearly a big jump in numbers, so I know it's not going to be arithmetic. It's going to be geometric. Anything with this big jump in numbers, clearly geometric, clearly not plusing by the same number. No way. I could see kind of easier right here between 15 and 5 that I'm dividing by 3. Some people do it that way. It looks like I'm dividing by 3, dividing by 3. I could look at that from 15 to 5. Other people take one of those two big numbers and divide by the one in front of it to see that, yes, 3. 3 is the number. I'm not timesing by 3. Nope. I'm dividing by 3, dividing by 3. But remember, we show dividing by 3 as timesing by 1/3. So that makes this tricky. I'm dividing by 3, but I don't show dividing by 3. I show timesing by 1/3. That is the same as dividing by 3, I promise you. So for the recursive function, I write f of x equals f of x minus 1. It's always like that for recursive, times, and I put that 1/3 right there. Never division, always timesing. If I want to show dividing by 3 each time, I show timesing by 1/3. All right, going backwards in this sequence, I'm doing the opposite of dividing by 3, which is timesing by 3, or the opposite of timesing by 1/3 is timesing by the flip-flop of that, timesing by 3. I'm taking this 35 and I'm multiplying it by 3. Should give me a bigger number. 135 times 3 gives me a bigger number, 405. Kind of makes sense because I can see the numbers are getting smaller from left to right. So 405, bigger number. All right, here we go. Explicit f of x. I take that green 405. This is geometric, never plussing in here. And I times it, showing parentheses now, times that 1/3, and I close that parenthesis, and I make sure I put that x in the exponent spot, so it's really small up there in the top corner. Exponential, one of these curvy graphs. All right, moving on. This guy right here, this is clearly going to be arithmetic. I know it's not geometric. I could see that these numbers are going down by about the same each time, not geometric. This is going to be a straight line situation going down like that. So if I take 55 and I take away 43, that will show me the number that I'm plussing for this one. I'm not subtracting, plussing. Adding 12 is the only number I could add to negative 55 to get a smaller amount of negatives, negative 43. So for this problem, I'm not subtracting 12, I'm adding 12. That makes this arithmetic going to be a straight line. For recursive, I write f of x equals f of x minus 1. And then don't put minus 12. This is plus 12, plus 12. That is my adding number. I'm adding 12. I'm not subtracting 12, adding 12. If I do this one to go back to the zero term, which I'd like you to be able to find, the opposite of adding 12 is subtracting 12. And what I'm subtracting 12 from is this negative 55. So you're taking negative 55 minus 12 should give me an even bigger amount of negatives, negative 67. You can see, kind of makes sense. Bigger negatives getting smaller negatives from left to right. So if I write this explicit function, this is going to be typical slope-intercept form with that 12, that change number right there in front of x. That's the change number, adding by 12 each time, 12x. And I put that y-intercept minus 67. That is the explicit form, clearly y equals mx plus b form for this. All right, so moving on. This one, writing explicit function using zero value, seeing that clearly it's a big jump right here. So it's not going to be a straight line. This is going to be one of these exponential ones. All right, so here we go. Taking 14 to 28. Some people could see that I'm timesing by 2. Some people have to take 28 and 14 to see that I'm timesing by 2. Either way, doesn't matter. I'm timesing by 2. Timesing by 2 makes this geometric, makes it curvy. If I'm going to the left on the pattern for this sequence, the opposite of timesing by 2 is dividing by 2. Dividing by 2. What am I dividing by 2? This 14 right here. So dividing by 2, which of course is the same as timesing by 1/2. Taking that 14, dividing by 2 gives me 7. That's the number I'm looking for. That's the number before 14. 7 times 2 is 14. Times 2 is 28. 28 divided by 2 is 14. 14 divided by 2 is 7. All right, so here we go. For my function, f of x equals, this is geometric, no plus and x in the exponent spot, 7 in parentheses, that red 2, and I close that, and I raise that to the x power, make sure my x is way up high up there in that exponential place. All right, geometric. Here we go, next one. Which one is geometric or exponential? Same thing, that's timesing. If you have any pattern that's timesing or really dividing, that's exponential. You're looking for the one that's timesing. So this one I could see is adding by 1. This adding by 8. This adding by 5. This is kind of wacky. There's nothing, no pattern there. This one adding by 1. adding by 2, adding by 3. Cool little pattern there, but that's not timesing. Adding by 2, adding by 2, adding by 2. Ooh, all going up by 2. This is the only real linear one I've seen so far. That would be like 2x. This one, not adding. Looks like I'm timesing by 3. Yep, 3 times 1. 3 times 3 is 9. Yep. 9 times 3 is 27. Yep, there we go. I'm timesing everything by 3. That is the one that's exponential in this little batch right there, a timesing one. All right, moving on. Number 11. For this one, look for all my exponentials first. I could see that the exponential ones with percents are this one right here. So that would be clearly number 1. I could see over here that I have another percent, so number 3. So I'm going to put number 1 and number 3 in the exponential section because I could clearly see they have this percent symbol. Easy, those are money. Now the other ones, look for something other that doesn't have a percent. This 20 is just plain old 20. There's no percent. So I'm going to take that and put that in the linear because there's no percent symbol right there. Just increasing by 20. That means I just keep adding 20, adding 20, adding 20. That's linear. If I look at the other ones, I need to see if they're linear or nonlinear. I'm done with my exponential. So now it's just either linear or nonlinear. So I have 9, 11, 13. Let's see this pattern. Looks like I'm going up by 2, going up by 2. Looks like going up by 2. Yep, that's going to be a straight line. That's going to be number 4, linear. All right, the hardest one on this is where you got to do a little math. So I take that 2 and that 28 and I divide them. So 2 divided by 28, or 28 divided by 2, I'm sorry, $28 for every 2 hours. That gives me $14 per hour. That's the rate. That would be like 14x for this equation. Another one, I look at these two numbers and divide those two. And if those two are the same as 14, I know this is linear. If it's not the same as 14, it's not linear. So if I take 42 and divide it by 3, that gives me $14 per hour. They both have the same rate of change for that little section. This is straight linear. So I put number 5 for this situation, linear. So none of these is neither. All right, moving on. For this guy, again, take this value right here and divide by the little one or the smaller one above it. I promise you, on a calculator, type in 457.96 and then hit the division button and then type in 428 and then hit the equal button. So 457.96 divided by 428 equals 1.07. That's the number that's going to be in parentheses for this exponential. That's the number that if I want to go from 428 to 457, that's the number I'm multiplying. 428 times 1.07 equals 457.96. Try it. All right, now I need to go up the table from this 1 here to go to really the 0 term in this sequence of numbers. So if I'm going up the table, I'm doing opposite of timesing by 1.07. That means I'm dividing by 1.07, and the number I'm dividing or typing in my calculator first is this 428. That will give you the number above 428. So if I take 428 on my calculator and I type that in first and I divide it by 1.07, my calculator will spit out what the number is above 428. So 428 divided by 1.07 gives me 400. That's the number above 428. Makes sense because 400 times 1.07 is 428 times 1.07 is 457.96. If I write this exponential equation, I take that 400, I write that first, I put in parentheses that 1.07, and I make sure I finish this up and put that x way up high up here in that exponential spot. Got to make sure I do that. That is the explicit function. That's going to be one of these curvy ones. All right, exponential, geometric. Here we go. This one, looking at an equation where for rent and deposit, kind of modeled after slope-intercept form, where the rent is the change number, the number in front of x. That's the rent for this situation, for this equation. The one-time deposit fee is going to be for this one like my y-intercept. For this one, the y-intercept, that's going to be the deposit for this one. So for the y-intercept, that is like the deposit. That's the one-time fee I'm paying. That 800 I'm paying each month. That's the change number. You're paying 800 each month. That's changing. The 700 is a one-time fee that you're paying. So what I'm looking for is which of these answers is describing that y-intercept number? The deposit, not the rent. That is the deposit. So for this one, find deposit fee that matches that 700. That's the y-intercept. That's what I'm looking for. That's the deposit fee on this one. All right, moving on. 14 for this one. All right, looking at these two categories, linear straight or curvy exponential. I could see for the number 14 clearly straight, so this would be linear. My next situation, dots. Is it dots or is it a line without dots? So I look and I could clearly see dots there. So that would be discrete, describing that data. Straight line, that data is going. Discrete, that data is. It's just dots, discrete. All right, next one in the middle, B. First category, straight or curvy. It looks like definitely curvy, so this one's going to be exponential. It's not straight. And then next category, of course, is it dots or is it a line drawn through the dots? And I can clearly see dots again. So this is discrete. Exponential data in that exponential pattern, that J curve, but dots, discrete. All right, next one. Here we go. First category, straight or curvy. And I could see, again, that one, see? This one's straight, so that one would be linear. Next category, is it straight dots or is it a line drawn through the dots? I see no dots for that one. So C, I call continuous data. Anytime you have a line drawn through all the dots, that's showing continuous data. All right, hopefully this helps. Good luck.